Welcome back to the deep dive. For anyone building or even just using software, there's this fundamental concept that really dictates whether an application scales smoothly or just grinds to a halt under pressure. It's like the invisible blueprint for performance. Today, we're doing a deep dive into BigO Notation. You've probably heard the term, right?
Oh, yeah, definitely.
So now let's really unpack how you can use it to evaluate efficiency. Okay, let's unpack this.
Exactly, yeah. At its core, BigO Notation tells you how the runtime, we call that time complexity, or maybe the memory usage, the space complexity.
Okay.
How that grows as the input size, which we usually just call n, gets bigger.
Right.
It's not really about the precise execution time, on your specific machine, but more about the rate of growth.
The trend line, almost.
Yeah, precisely. And we tend to focus on the worst case scenario. It simplifies things too, because we ignore constant factors and terms that become less significant as n gets really large.
Okay, so like if you had an example.
Sure. So imagine an algorithm's runtime is, let's say Tn equals 4n squared plus 100n plus 500.
Okay.
Its big O is just O and 2. Because that n squared part, that's what really dominates everything else when n gets big. The 100n and the 500 just don't grow nearly as fast.
That's a really powerful way to think about it. It's like learning to see the underlying growth behavior in the code itself.
Exactly.
So I think our mission for this deep dive is to equip you, the listener, with the ability to spot that pattern, helping you understand what makes code truly efficient, not just for small tests, but when it's dealing with huge amounts of data.
Right.
And we'll be breaking down exactly how you analyze BigO, like directly from the code.
Yeah. And if we connect this to the bigger picture, mastering this skill, it really allows you to reason about fundamental efficiency. It's crucial. So we'll look at analyzing, individual operations, understanding how loops contribute different kinds of loops.
Yeah, loops are a big one.
Oh, yeah. And then how to combine those complexities when you have different parts working together in your code.
Okay, let's start there then. With the basics, you mentioned individual operations. What does that actually mean for BigO? And where do people sometimes get tripped up, maybe thinking something's constant time when it isn't?
Right. Well, simple statements, things like assigning a value to a variable.
X5.
Exactly. Or doing basic math like addition or subtraction. Or, importantly, accessing an element in an array if you know the index, or in a hash map using its key.
Okay.
Those are all generally considered O1. Or constant time. What that means is the time it takes, the number of steps, it doesn't really change no matter how big your input in gets.
Stays
flat. Because those data structures, arrays and hash maps, they offer direct, immediate access. But you mentioned getting tripped up.
Yeah.
A common one is the linked list. If you want to get the element at, say, position 1000 in a linked list.
You have to walk the list.
You have to walk the list. You have to start at the beginning and go step by step by step. So in the worst case, accessing an element by position in a linked list is actually ON, linear time, not O1.
That's a fantastic distinction. So for you listening, that means even if that list is unimaginably vast, getting element 5 from an array is still just like one step, same speed. That's powerful.
It really is.
Okay, so O1, constant time, feels pretty intuitive once you see that linked list catch. But where things get really interesting and sometimes painful for performance is when we start introducing loops. What's the fundamental impact there when your code starts iterating? And are there common traps?
Yeah, loops are where complexity often starts to climb. So if you have a simple loop that just runs on any n times, meaning it iterates once for every item in your input.
Like printing every item in a list.
Perfect example, that's OHEN, or linear time. The runtime grows in direct proportion to the input size. Double the list size, you roughly double the time it takes. The trap here sometimes is maybe overlooking what's inside the loop. Even if the operations inside seem small, doing them in times can add up. But the overall pattern is linear growth.
Okay, linear. Double the input, double the work. Makes sense. But my intuition and probably some painful memories tell me that nested loops are where things can really explode.
Oh, absolutely. You're right to focus on that.
Can you walk us through why that multiplication happens? Why is it so dramatic? For someone who might not immediately see that jump from linear to, well, whatever comes next.
Right. So nested loops, they multiply their complexities. If you have an outer loop that runs n times, and inside that loop, of every single one of those n iterations, you have an inner loop that also runs n times, Yeah. You end up doing n times n operations. So that's ONN, which we simplify to ON2, quadratic time.
Quadratic.
And the runtime is now proportional to the square of the input size. The reason it jumps so much is, like you said, for every single item the outer loop looks at, the inner loop has to go through the entire list again.
So n operations n times.
Exactly. N times n. So if you have, say, 10 items, that's 10 times 10, 100 operations. Not too bad, maybe.
Right.
But if you have 1,000 items, that's 1,000 times the 1,000. That's 1,000,000 operations.
Wow.
The source material mentions an example, like a find duplicates function, where you might compare every item to every other item. That's a classic ON2 scenario.
Okay, so if your input size doubles, say, from 1,000 to 2,000 items, the operations don't just double, they go up by a factor of 4. 2,000 squared is 4 million.
Precisely. They quadruple. That's a huge difference in performance.
I can practically hear the server fans spinning up just thinking about large data sets with n-squared algorithms.
Yeah, I've definitely seen situations where a really clever application idea just completely grinds to a halt in production because someone missed a hidden ON2 loop during development. It can be a silent killer for scalability.
Definitely something to watch out for. So we have constant, linear, quadratic. Are there other common performance signatures, maybe less dramatic than quadratic, that we should know about?
Yes, absolutely. There's another really important one, O log n, or logarithmic time.
Logarithmic? That sounds efficient.
It's incredibly efficient. It often shows up in algorithms where the problem size is effectively cut in half with each step.
Okay.
Think about loops where the control variable, the counter, isn't just incrementing by 1, but maybe it's being multiplied or divided in each step. Those are often logarithmic.
Right. Tell us more about O log n. It sounds almost magical compared to ON2. What's the core idea and what's a classic example?
Well, it's so efficient because, as I said, you're drastically reducing the scope of the problem with every single operation. The classic textbook example is binary search.
Searching a sorted list.
Exactly, like searching for a word in a dictionary. You don't start at A and read every single word.
No, you'd open it somewhere in the middle.
Right. You open roughly to the middle, see if your word comes before or after that page,
Yeah.
and then you essentially discard half the dictionary. You keep having the remaining section until you pinpoint the word. So for an input of size and say, and pages in the dictionary, you can only cut it in half about log base 2 on the long times before you're down to just one page or one element.
Okay, so the number of steps grows much, much slower than the input size.
Way slower. Doubling the input size only adds roughly one extra step. That's why it's so fantastic for searching or working with large, sorted data sets.
That makes perfect sense. Okay, so we've got O1, ON, ON2, and a log n.
Yeah.
What happens if you have, say, a function that does a bit of linear work and then maybe does some constant time stuff afterwards? How do we combine these?
Good question. When you have sequential blocks of code, like do this, then do that, you generally add their complexities.
Okay.
So if you have an ON loop followed by, say, an ON2 nested loop, the total complexity is technically ON plus N2.
Right.
But remember how we ignore less significant terms?
So the N2 still dominates.
Exactly. For large values of n, the n2 term grows so much faster than the n term that the n term becomes almost negligible in comparison. So on plus n2 simplifies right back down to just on2. You always keep the largest, most significant term.
Got it.
And that's crucial because it means one inefficient part, maybe one nested loop hidden somewhere, can totally dictate the overall performance of your entire function or algorithm.
Wow. So boiling it all down then, the central takeaway here seems to be that mastering BigO notation isn't really about counting every single exact process or step. It's more about learning to see the scaling pattern in your code.
Precisely.
When you look at an algorithm, maybe the key question you should ask yourself is, if my input size doubles, what happens to the number of operations? Does it stay the same? Does it double? Does it quadruple? Or does it barely budge?
That's the heart of it. And what's fascinating here is how these distinct scaling patterns reveal an algorithm's true efficiency and, importantly, its limitations. Like you said, if operations stay the same when input doubles, that's O1, constant time. Rock solid. If operations double, it's ON linear time, predictable scaling.
Okay.
If operations quadruple when input doubles, that's ON2, quadratic time. Danger zone for large inputs.
Definitely.
And if operations only increase by maybe one step when the input doubles, that's that super efficient O log n logarithmic time.
Yeah.
Each of these represents a fundamentally different way an algorithm behaves under pressure. It defines its performance curve.
So what does this all mean for you listening to this?
Well, I think understanding BigO is just a fundamental skill. It lets you write code that's not just correct, but also efficient and scalable. And maybe just as importantly, it helps you reason about the trade-offs between different approaches before you even start coding. You can predict potential bottlenecks.
Makes sense. Saves a lot of pain later.
Absolutely. And maybe this raises an important question to leave you with. Knowing what you do now about these scaling patterns, how might you start to critically evaluate the performance of the software you use every day? Or even think about systems in your own life that process information. How do they scale?